the velocity and acceleration, we will going to cover the types of motion, that is a rectilinear motion, pure rotational motion, curvilinear motion, and velocity and tangential acceleration and Carol's component of acceleration. So first motion we have is a rectilinear motion. A motion that takes place along a straight line is called as rectilinear motion. So we have a block here is resting on this surface. So this type of motion is called as rectilinear motion. The velocity will be equals to v and it has only one acceleration, that is called as tangential acceleration. So rectilinear motion is defined as the motion along a straight line and the direction of motion is parallel to the plane. So all your Newton's laws of motion, that is v is equals to u plus at, is basically the tangential component. Square equal to u square plus twice as. So this a is basically tangential, or s equals to ut plus half at square. So this equation involves only tangential component. The second motion is called as curvilinear motion. In a curvilinear motion, the particle can describe any path, that is along a curve. And suppose we consider this part, at this point it has a tangential velocity in this direction. So it has a tangential velocity, it has a tangential component, and it has a normal component. But when the particle will come to this point, it has a tangential velocity in this direction. Same will be the direction of tangential velocity, and the normal direction will be like this. So every time the component has center of radius. So here the center of radius is from this point to this point. That is called as radius of curvature. Somewhere here we have different radius of curvature like this. So rho is called as radius of curvature. V is called as tangential velocity. At is called as tangential acceleration. An is called as normal acceleration. And this v and at, they are same as the rectilinear components. Only difference is that an is called as normal acceleration and is always direct towards the center and is given by v square divided by radius of curvature rho. Is given by omega multiplied by radius of curvature whole square, that is the tangential velocity, multiplied by rho. So is also given by omega square multiplied by rho. So at any instant of time, your acceleration tangential will go this way, normal will go this way, and therefore the resultant component will go this way. So this one is tangential component, this one is normal component, and this one is total acceleration. So total acceleration is always obtained by vector sum, that is the at square plus an square. And the third type of motion we have the pure rotational motion. It is a special case of curvilinear motion. In the rotational motion, the particle has fixed, particle is rotating about the fixed radius. So value of rho become constant and that equals to r. If the particle is rotating in a clockwise direction, then at any instant of time the velocity is perpendicular to path. So this component has also another component of a acceleration that equals to an. So this one is at and this one is an. And a is same as at square n square and the an will be same as omega square r. So this time we can model this one as the rigid body motion. It is rotating at angular speed equals to omega. So suppose we are given here one link, let's say OA is the link, and this link is rotating at a constant angular velocity equals to omega. So if omega is constant, then the value of alpha, that is d omega by dt, is always zero. So it does not have any type of angular acceleration. The velocity vector you have to draw in the same sense as that of omega, and the value of this velocity at point A is entirely dependent on the distance of point A on this link. Suppose this value is equals to OA, VA equals to OA multiplied by omega. What is the point is change? That is, we take different point that equals to B. So this time this value equals to VB is equal to omega multiplied by OB. If I continue this way, then as I approach to the lower point, is my velocity, is vector is going to change, and finally 0. So as the point is moving away from the hinge, velocity will become maximum, and if you draw this one, you will get a straight line. So they are proportional quantity, and proportional omega is constant. So this equation is same as y is equal to mx, and that distance will be equal to the distance from origin. If you consider the same link, but this time we will only discuss for acceleration. This is the value of alpha is 0. So tangential acceleration is normally given by at is equals to alpha multiplied by radius r, similar to tangential velocity equals to omega multiplied by r. So alpha equal to 0. So tangential velocity at all these points will be equals to 0. But is all these points have the normal acceleration? And what is the normal acceleration is given by v square by r or va square by r. So this point is A, so it will experience an, and this Vn equals omega square multiplied by the distance of this point from O. Net velocity at this net acceleration at this point is same as A, so this value itself equals to resultant acceleration A. So in pure rotational you don't have AT. What is AT is 0, but we do have tangential velocity. So is the acceleration of point A is different, and is the acceleration of point B is also different? B is also different. What is the acceleration of B? So this time acceleration of B will be An equal to omega square multiplied by OB. So all these accelerations are different. Tangential velocity will be different. So if the relative velocity exists between point A and point B, how much is relative velocity? That you can calculate using this difference. So velocity of A with respect to B is this value. What is this value? Is it VA minus VB? Or if you talk about A to B, in that case you have to locate from this side. So is this vector will be leftward vector. So this time velocity of B with respect to A. Velocity of point O is 0. If the velocity at point O is 0, or this velocity will be called as absolute velocity. VA will be called as absolute, VB will be called as absolute velocity, because one reference was equals to 0. For this 4-bar mechanism, the centers are represented by O1 and O2. This one is link number 1. This one is link number 2. This one is link number 3. This one is link number 4. So is the motion of link O1A is pure rotational motion. This one is pure rotational motion. Is the motion of link number 4, that is O2B, is it pure rotational motion? And when we have a pure rotation of this and pure rotation of this, so is the motion of this one is a complex motion, is a translational plus rotational motion. So this motion is purely rotational, this motion is purely rotational, and this motion is rotational plus translational. So this is called as general motion. For this 4-bar mechanism, so is the motion of link O1A is pure rotational motion. This one is pure rotational motion. Is the motion of link number 4, that is O2B, is it pure rotational motion? So is the motion of this one is a complex motion, is a translational plus rotational motion, and this motion is rotational plus translational. So this is called as general motion. Okay, let's consider here one link that is represented as AB, and after some time this link, let's say this position. So point A has come to here and B has come to this point. Let this point is B dash and this point equal to A dash. This link has been turned like this, and somewhat is what translate also, so that you have to investigate. What we do is that we'll try to analyze this motion. So let's first assume that the link AB is here, and let's say the link has translated this motion. So because it has shifted the position, so we have pure translation motion. And then with this is the basic motion right now, that is this instant. And then what we'll do is that we'll rotate it. Now in the second instant, is it a pure rotational motion? We'll repeat this. And this time is this point is A dash and B dash is the same as this situation. So is your general motion is basically consists of translational plus rotation. To try to understand this concept, general plane motion can be considered as a pure rotational motion about a point called as IC. Suppose I draw a vertical line through this point, and if I draw another axis line like this, so is this point is temporary, basically is representing what? The IC. And you can imagine that this entire motion takes place about this point. IC is that point where velocity is 0. So this figure and this figure, is it same as this figure? So temporarily we can assume that this link is hinged at this point, and you can model this one as a pure rotational motion. But anytime if your position has been changed, the IC will also change. So IC is a free or IC is variable here. So the link as a whole is considered to be rotating about an imaginary center at a given instant of point that we called as IC point. And what is the velocity of this one? Velocity at this point will be equals to 0. Now though I have shown my IC outside here, IC can be inside or IC can be outside. So IC you can locate IC you can locate just by drawing two perpendicular vectors. Suppose we know the velocity at this point and we know the velocity at this point. Suppose you know the velocity vectors and their magnitude. So we can draw one perpendicular to this velocity vector. You draw one velocity vector perpendicular to this one. Where this perpendicular will intersect, that point will be equals to IC. That is a simple method for IC. But you should know the velocity. And opposite, if you know the IC, can you find out the velocity at that point? We have two sliding prismatic pair, two rotating pair, and let's say that this slider is going this way with a certain velocity equals to V. Let's say VA. Let's say this point is A point. Let's say this point is B point, and the distance between these 2 points is known to us. So he has given us this distance. Let's say this distance equals to 3. Let's say this distance equals to 4. Now from this figure is very clear that this slider will also go downward. So this slider will go downward. So you know the velocity vector. The direction of velocity vector is known to us. This velocity vector he has given to us, and this velocity we can find out, or we can get the idea of this velocity vector. So this velocity vector is VB vector. So what you do is that you draw perpendicular to this velocity vector because you know the direction, and where it will intersect that we don't know. And you draw one velocity vector to this one. You draw one perpendicular to this velocity vector. These two velocity vectors will intersect at a point. Where they intersect, then that point will be called as IC. So temporarily you can assume that this member and this member, these two velocity vectors will route about the point C with a constant angular velocity omega. This motion of this link is a translational plus rotational motion. So this link has angular velocity equal to what? Omega, about the point C. Now this distance from B to C is equal to 4, and this distance from IC to this A point is equal to 3, and omega is constant value. Now since omega is a constant value, can we write omega equal to this velocity VA divided by perpendicular distance between these 2 points is equal to 3, is same as velocity of B. Velocity of B at this one will go this way having omega value, and distance equals to what? 4. So if you know the VA, suppose I say VA equal to 5 meter per second, can we calculate velocity at point B? So velocity at point B can be easily find out, that equals to VA equals to 5 multiplied by 4 divided by 3. So within a fraction of a second, with the method of IC, we can solve the problem. As the link moves, its IC changes from one point to another point during its motion. The locus of IC of a link during the whole motion is called centroid. In general, the centroid is a curve or a straight line. Now check this concept, what this concept is. Suppose right now the slider B is here and slider A is here, so IC is at this point. And suppose this slider will move downward, that is here. So this slider will go rightward, and because of this one, if you draw the horizontal line to this and vertical line to this, IC will change. So if you draw all these points somewhere like this, if you draw all this one, you get a curve. That curve is called as centroid. So centroid basically represents what? Locus of IC. Approaches. First approach is a graphical approach, and second is IC approach. And before this, we have to find out number of ICs. Is given by n multiplied by n minus 1 divided by 2, where n is number of links. So for 4-bar mechanism, number of ICs will be 4 multiplied by 3 divided by 2 is equal to 6. And when you are labeling IC, you label I, and always write lower number first and then higher number. So one combination is 1 2. 1 2 is same as 2 1, but do not write 2 1. Lower letter first, lower number first, then second number. Then we have second combination is I1 3. Third combination is I1 4. So one combination has been exhausted. So we have 2 3, and then we have 2 4. So 2 combinations over, one combination is left, 3 4. So it is job to locate IC first.